We next look at the situation where we want to compare the means of two populations, but where the population variances are unknown and it's not reasonable to assume that the population variances are equal. And so because of that, because the population variances cannot be assumed to be equal, we have to go on the assumption that they're different. And so in that situation, we would not pool the sample variances to get a pooled sample variance because it would not be estimating the correct quantity. And so we have to utilize the sample variances separately, as we do here in this test statistic. The formula for the test statistic, which we're going to again call t-calc, is in the numerator the difference between the sample means, which is a point estimate, an unbiased estimator of the difference in the population means. From that we subtract the hypothesized difference delta 0, and then we divide that difference by the estimated standard error of the difference in the sample means. And that estimated standard error is, you can see here, the square root of the variance of sample 1 over the size of sample 1 plus the variance of sample 2 over the size of sample 2. Now, that test statistic is not hard to compute, but the problem arises in that we don't know the actual sampling distribution of this test statistic under the conditions of the null hypothesis. We do know that it has a t-distribution, but the degrees of freedom of that t-distribution are unknown. Now, the degrees of freedom can be approximated, and there are several ways to do that. One method of approximation of the degrees of freedom is to use what is called Satterthwaite's approximation, but that's rather involved computationally, and it's not an approach that we would use by hand. Now, there's another approach that we could use, and it's an approximation that gives us a conservative test in the sense that the it will result in a test whose significance level is less than or equal to the desired significance level alpha. And we'll see that on the next slide. But before we go there, I will just say that one approach to performing this kind of a test, if the sample sizes are both greater than 30, would be to use the standard normal distribution as the reference distribution. Because in that case, when both of the sample sizes exceed 30, then the sampling distribution of t-calc under the conditions of the null hypothesis is close to being, it's close to the standard normal distribution. Now, in doing this by hand, we're going to, if the sample sizes are not both greater than 30, then we'll have to come up with some kind of an approximation technique for the degrees of freedom. And the approach that we'll use, at least when we're doing this by hand, is to use the following approximation or the following calculation for the degrees of freedom. We will use the minimum of the degrees of freedom associated with the two samples. So you'll remember that if the size of sample 1 is n1, then we have n1 minus 1 degrees of freedom associated with sample 1. And if n2 is the size of sample 2, then the number of degrees of freedom associated with sample 2 is n2 minus 1. And so the approach that we will use to approximate the degrees of freedom is to use the minimum of those two values. Now, we know that that's not the true number of degrees of freedom, but like I said, doing this approach will give us a conservative test in the sense that the true significance level of the test will be no more than the desired significance level. Now, you'll remember that if we use a smaller significance level, what that does is decrease power, and so that's why this is conservative. We know that we are going to be preserving the significance level. The true significance level will be no more than what we are wanting it to be, but we do understand that that will come at a perhaps, hopefully, just a slight reduction in power. So again, looking at the rejection criteria, we have the same three types of hypotheses. We have the two-tailed test, the left-tailed test, and the right-tailed test. And so you see here that the rejection criteria are the same as they would be for really any other t-test. The only difference is how we compute the degrees of freedom in this particular situation. Now, this is what we would do if one or both of these sample sizes is not greater than 30. If both sample sizes are greater than 30, then we could just use the standard normal distribution to get our critical points. And so then we would have z-values here for the critical points. So let's look at an example. This is an example involving surveys of commuter attitudes. So in a study on attitudes among commuters, random samples of commuters were asked their feelings toward fellow passengers using a score ranging from 0 for like to 10 for dislike. And so here we have a Likert scale from evidently 0 to 10. 0 means like, 10 means dislike, and so we have that range of integers in between 0 and 10. A sample of 10 city subway commuters, and so we'll let the population of city subway commuters be population 1, and we'll let population 2 be the population of suburban rail commuters. And so we have a sample of 10 city subway commuters from population 1, and an independent sample of 17 suburban rail commuters, so a sample of size 17 from population 2 that we're using for this study. The purpose of the study is to compare the mean attitude scores of the two types of commuters. It can be assumed that the data represent samples from normally distributed populations. Now, let me just say a couple things. Number one, we see that both sample sizes are less than or equal to 30. And so we're in coming up with the critical points, we're going to have to use the t-table, and we will use the approximation that we have for the degrees of freedom, which would be the minimum of the degrees of freedom associated with the two samples. And so sample 1 has 10 observations, so there are 9 degrees of freedom associated with that sample. Sample 2 has 17 observations, and so there are 16 degrees of freedom associated with that sample. And so the minimum of those two values would be 9, and so we would be using the t-distribution with 9 degrees of freedom from which to get our critical points. Now, the other thing I would say is that because the possible values that the random variables can take on are essentially the integers from 0 to 10. We know a priori that the normal distribution is not appropriate here. But we're just going to go ahead and kind of pretend that that's the case. Ideally, if we had a larger sample, then we could appeal to the central limit theorem. But the samples are not that large here. But if the populations are really not too terribly skewed, then samples of size 10 and 17 actually may be adequate for the central limit theorem to kick in. So anyway, we're going to go with this assumption, but I just wanted to point that out. Okay, so here we have the summary statistics. So again, sample 1 has 10 observations. The mean score for sample 1, so this was the city subway commuters, their score was 3.7. The standard deviation for that data set was 3.623. The sample for the suburban rail commuters we have 17 observations. We surveyed 17 people, evidently. The mean score there was 1.53, so it is smaller, it is lower than the mean for sample 1, and it's got a standard deviation of 1.463. And so you can see that there is quite a difference here between the two sample standard deviations. And if what we could do is we could test the null hypothesis that the population variances are equal, and I would actually recommend that you do that. But for the sake of this example, we're going to assume that the population variances may in fact be different. We're not going to a priori assume that the population variances are equal. And so we're going to perform a comparison of the population mean commuter scores for the two populations using the approach that we're looking at in this section. And we're going to do that test at a 0.05 level of significance. In addition, we're going to construct a 95% two-sided confidence interval for the difference in the population means. And so, actually, I see here that I am doing the comparison of the population variances. So the question would be, is it reasonable to assume that the population variances are equal? And so let's let sigma 1 squared be the variance of the scores for the population of city subway commuters, and sigma 2 squared be the variance of the population of suburban rail commuters. The hypotheses to be tested are then given by the following. The null hypothesis being that sigma 1 squared is equal to sigma 2 squared, right? Or equivalently, that the ratio sigma 1 squared over sigma 2 squared is equal to 1, against the alternative that the two variances are not equal, which is equivalent to the ratio of the population variances being not equal to 1. And the test statistic for this is the ratio of the sample variances. And we're going to perform this test at a 0.05 level of significance, just like we're going to use for comparing the means. And this is a two-tailed test. And so the rejection criteria would be to reject the null hypothesis if the test statistic F-calc is either less than 0.267 or if it's greater than 3.05. And we see here that, and I have a typo here, but this should be 0.1463 inside here. And so we see here that the ratio of the sample variances is 6.134. And because that is greater than 3.05, we would reject the null hypothesis. And so there is sufficient evidence at the 0.05 level of significance to conclude that the population variances of the scores are different. And so it's not reasonable at the 0.05 level of significance to assume that the population variances are equal. And the reason for that, the reason that it's not reasonable to assume that, is because we reject that assumption. That assumption is right here in the null hypothesis. That is it reasonable to assume this? Well, no, not at the 5% significance level, because we just rejected that null hypothesis. All right, so let's proceed now and let's compare the population means. So we'll let mu1 denote the mean attitude score of the city subway commuters, and mu sub 2 be the mean attitude score of the suburban rail commuters. The hypotheses to be tested are as follows. The null hypothesis is that the two means are equal, which can be equivalently stated as their difference being equal to 0. And the alternative is that the two population means are not equal, which is equivalent to the difference being not equal to 0. And again, we're going to use a significance level for this test of 5%, alpha equal to 0.05. The formula for the test statistic, the difference between the sample means minus the hypothesized value of that difference, which is 0, divided by the estimated standard error of the difference in the sample means. And so the square root of S1 squared over N1 plus S2 squared over N2. Now, the degrees of freedom for the two samples are 9 and 16, as we indicated previously. Since the actual number of degrees of freedom would be somewhere between 9 and 16, using the minimum of these two values as the degrees of freedom for the test will result in a conservative test. Now, the rejection rule would be to reject the null hypothesis if t-calc is either less than negative 2.262 or if it's greater than positive 2.262. All right, now we take these sample summary statistics that have been given, we plug them into the formula for the test statistic, and we find that t-calc is equal to 1.8093. And so our conclusion, since the rejection criteria have not been met, in other words, because 1.8093 is not less than negative 2.2622 and 1.8093 is not greater than positive 2.2622, we fail to reject the null hypothesis. And so there is insufficient evidence at the 0.05 level of significance to conclude that a difference exists in the mean attitude scores for the two types of commuters. So that's how we use this procedure. And you see, really the only difference between this and the other situations we've looked at is how we come up with the degrees of freedom for the test. Okay, now we get into the next section. Hypothesis test for two population means with dependent samples. And I think what I'll do, I'm going to save this for the next lecture video. I want to keep this one fairly short, so we'll pick this up in the next lecture.